Hey everybody, and welcome back to AI.Code.Cast. We're diving deep into an awesome coding problem today.
Oh, yeah. This one's a classic.
It's all about word replacement and how to get creative with algorithms to make it happen.
And as always, it's super interesting to see how the right data structure can totally change how efficient your solution is.
You hit the nail on the head there. All right, so let's set the stage for our listeners. Imagine you have a dictionary of root words, just like a regular dictionary,
Yeah.
but we're only focusing on the root words.
Okay, I'm with you.
So let's say our dictionary has cat, bat, and rat for now. And we also have a sentence, something like, the cattle was rattled by the battery.
I see where this is going.
The challenge is to replace each word in that sentence with the shortest root word from our dictionary that forms its prefix.
So cattle would become cat, rattled would be rat, and battery turns into bat.
Got it. You got it. It's like
Yeah.
we're simplifying the sentence using our limited vocabulary.
Makes sense.
Now, my first instinct is to just go through each word and chop it up into all its possible prefixes. Like starting with the first letter, then the first two, and so on.
Yeah, and then see if any of those prefixes match a word in the dictionary.
Exactly. But I can already see how that could become a problem.
Oh, yeah, especially if you've got a huge sentence or a massive dictionary.
Right. It feels super inefficient.
It's the brute force method.
Yeah.
Straightforward, but definitely not the most elegant.
Okay, so brute force is out. But before we move on, are there any potential, tricky situations we need to think about? Edge cases?
You bet. Like, what about upper and lowercase letters? Should cat and cat be treated the same?
Good point.
And what if a word has punctuation in it, like cat-like or rattle.snake? Those could throw a wrench in things.
Those are definitely things to consider.
Yeah.
We need a solution that can handle all those weird cases.
Exactly. Got to make sure it's robust and can handle anything we throw at it.
So assuming we figured out those details, let's get back to finding a better approach than brute force. That brute force method feels like we're trying to kill a fly with a sledgehammer.
Uh-huh. I like that analogy.
So what if we had a way to quickly check if a prefix is actually a valid root word from our dictionary? Like instantly know without comparing it to every word in the dictionary.
Now you're talking. That's where a cool data structure called a hash set swoops in to save the day.
A hash set. Okay, I'm listening.
Think of it like a bag of words. But each word in the bag has to be unique. You can quickly chuck a word in there and instantly see if it's already there.
So we're talking super fast checking.
Exactly. And it doesn't matter how many words are already in the bag. Checking is always super quick.
So if we load up our dictionary into a hash set, we could just quickly check if any prefix we create from the sentence is a root word.
Exactly. That's way faster than the brute force method.
Definitely sounds like it. And wait a second. If we find a matching prefix in the hash set, we know it's the shortest root word for that word, right? Because we're checking from shortest to longest.
Boom, you got it. No need to check any further prefixes. It's like finding the perfect shortcut.
Shortcuts are the best. But hold on, are there any downsides to using hash sets? Like, do they take up a lot of memory?
You always got to think about the trade-offs. Setting up a hash set takes a little bit of time and memory, depending on how many words are in your dictionary.
So the bigger the dictionary, the more memory the hash set will need.
Right, but the cool thing is we only do this once at the very beginning. Then we can reuse that hash set for as many sentences as we want.
Like a one-time investment that keeps paying off.
Exactly.
Okay, I'm starting to like this hash set idea. But if I were to actually do this, how would I go about it step by step?
First, you'd make an empty hash set. Then, you take each word from your dictionary and add it to the hash set. This makes sure you only have one copy of each root word.
So far, so good. What's next?
Next, you break down your sentence into individual words.
Okay, I'm with you.
Then, for each word, you go through all possible prefixes, starting with just the first letter.
And then the first two letters, then the first three, and so on.
You got it. And for each prefix, you just check if it exists in your hash set.
Got it. So we're checking if any part of the word matches one of our root words. Then what?
If you find a match, you replace the original word with that matching prefix from the hash set. And remember, you can stop checking prefixes as soon as you find one.
Right, that early exit strategy.
Right.
Okay, what if you go through all the prefixes and there are no matches?
Then you just keep the original word.
Oh, okay. That makes sense.
It means there's no root word in our dictionary that can simplify it.
All right, I'm liking this hash set approach more and more. It seems way more efficient than our brute force idea.
Definitely.
But you know me, I always wonder if there's an even better way. Is this the most efficient solution out there?
There are actually other ways to do this. One that comes to mind uses a special data structure called a trie.
A trie. I've heard of those. They sound kind of mysterious.
They're cool.
But maybe before we dive into the world of tries, we should take a closer look at how efficient our hash set solution really is.
Yeah, let's talk about time complexity. It's super important to know how well an algorithm performs.
Time complexity. Break it down for me. What exactly does that mean?
Basically, it tells us how the runtime of our algorithm changes as we give it more and more input.
Okay, so if we have a super long sentence or a gigantic dictionary, how will that affect our hash set solution?
In the absolute worst case scenario, where none of the words in the sentence have matching prefixes in our dictionary, our algorithm would end up checking every possible prefix of every single word.
Yikes, that sounds like a lot of checking.
Yeah, and in that worst case, the time complexity would basically be how many words are in the sentence multiplied by the average length of those words.
So if we double the length of our sentence, we double the work for our algorithm.
Pretty much. But remember, that's the worst possible case.
Hmm.
In reality, we'd expect to find matching prefixes pretty early on.
Right, because of that shortcut we talked about.
Yeah.
So the average performance is probably much better.
Yeah, you got it.
Okay, that makes sense. So we've talked about how long it takes, but what about memory? Does the hash set use a lot of memory, especially with a big dictionary?
Great question. That's what we call space complexity. And the main factor here is the hash set itself. It holds all those root words.
So bigger dictionary means more memory for the hash set. That makes sense.
Exactly. It's important to think about both time and space complexity when comparing different solutions. Sometimes a slightly slower algorithm that uses less memory might be the better choice.
Okay, I'm starting to see the big picture here. It's like balancing speed and memory. But I'm still curious about those tries you mentioned.
All right, let's get into it. A trie, sometimes called a prefix tree, is a data structure specifically made for finding prefixes quickly.
So how does that work?
Imagine a tree where each node is a letter, and branches connect those letters to make words.
So if we had cat, bat, and rat in our trie, the first level would have nodes for C, B, and R.
You got it. Then under C, you'd have A, and then under that T, marking the end of the word cat, and you'd do the same for bat and rat.
Okay, I see how that tree shape would help us find prefixes. But how would we actually use a trie to solve our word replacement problem?
So imagine our dictionary is stored in this tray. For each word in our sentence, we follow a path down the trie, going letter by letter.
Hmm.
And if we hit a node that marks the end of a word, we know we've found a valid root word. That's the prefix we're looking for.
It's like the trie is a map leading us to the shortest root word for each word in our sentence. I like that visual.
It's a good one.
But creating a trie sounds a bit more complicated than a hash set.
You're right, it takes a bit more work up front. You got to go through each word in your dictionary and create the nodes and branches in the trie.
So more setup time, but potentially faster searching in the long run? That trade-off again.
Exactly. And a trie is even more efficient if our dictionary has a lot of words with shared prefixes.
Yeah.
Like if we had cat, cattle, and caterpillar, the trie only stores cat once and then branches out for the other parts.
So it's saving space by only storing the shared part once. That's clever.
Yeah.
But what about that early exit strategy we talked about with the hash set? Can we do that with a trie too?
That's a great question. And it really shows how cool tries are. Because we're moving through the trie one letter at a time, the moment we hit a node that marks the end of a word, we've found the shortest route and we can stop.
Wow, so the trie itself has that shortcut built in? We don't need a separate hash set to keep track.
Exactly. The trie is like a multi-tool. It does both the searching and the early exit all in one.
Okay, I'm impressed. But let's talk efficiency. How does the trie approach compare to the hash set in terms of time and space complexity?
Good question. Let's break it down. For time complexity, in that worst-case scenario where we don't find any matching prefixes, the time to search is basically how many letters are in our entire sentence.
So a sentence with 1 million letters would take about 1 million operations.
Yep. But that's the absolute worst case. In most cases, we'd find those matches way sooner.
Okay, so not as bad as it sounds. But didn't we say something similar about the hash set? That its time complexity was also about how many letters were in the sentence.
You're right, but there's a subtle difference. With the hash set, in the worst case, we might end up checking all possible prefixes of each word against the hash set.
Okay.
So a 10-letter word could mean 10 checks against the hash set. But with a trie, we just move down the tree once, letter by letter, which can be way faster, especially for longer words.
I'm seeing the advantage here. It's like the trie is taking advantage of those shared prefixes to make the search super efficient. What about memory usage? How does the trie compare to the hash set?
Another great question. It really depends on what our dictionary looks like. If it has a lot of words with shared prefixes, the try could actually use less memory than a hash set.
Wait, really? I would have thought a tree would always take up more space.
That's the cool thing about tries. Because they share those prefixes, we don't have to store the same letters over and over again.
Oh, I get it. So if our dictionary has a bunch of words that start the same way, the try will save us memory compared to a hash.
Got it.
Okay, I'm really starting to understand the trade-offs here. Choosing between a hash set and a try is all about what kind of dictionary we have and what we're trying to achieve.
It's like choosing the right tool for the job.
Exactly. But you know me, I always like to think outside the box. We've seen the strengths and weaknesses of both hash sets and tries. Could we somehow combine them? Could we create a hybrid solution that takes the best of both worlds?
Now you're talking. That's a fantastic question, and it opens up a whole new world of possibilities. What if we could use the speed of a hash set and the efficiency of a try?
That's what I'm talking about. It's like we've got these two powerful tools, and I want to see if we can merge them into something even more awesome.
I like the way you think. Let's dive into that in the next part of our deep dive. Stay tuned.
Welcome back, everyone. We're in the middle of figuring out the best way to tackle this word replacement problem.
And we're about to unlock the secrets of merging hash sets and tries.
That's right. But before we get too carried away with that hybrid idea, you left us hanging with this question. Could we combine the speed of hash set lookups with the efficiency of try traversal?
It's definitely a tempting thought. Blending the best of both worlds. Right?
Exactly. But before we get lost in that rabbit hole, you also mentioned something about how the dictionary itself can influence our choice of approach.
Absolutely. It's something people often forget. The kind of data you have can totally change which algorithm works best.
So let's say we have a dictionary full of short words, like 2 or 3 letters each. Would that change our strategy?
For sure. In that case, the hash set might be the way to go. Remember, setting it up has a one-time cost based on how many words are in the dictionary.
Right.
But if those words are short, the try wouldn't have much chance to show off its prefix sharing magic.
So with a bunch of short words, building a try might not be worth the effort.
Exactly. Plus, the hash set's super fast lookups would really shine in that scenario. It'd be like having a turbocharged index for our dictionary.
Okay, makes sense. So it's all about picking the right tool for the job. What about the opposite scenario? A dictionary packed with super long words, like scientific terms.
Now that's where the try would really shine. Longer words mean more chances for shared prefixes, and that's where the try saves a ton of space.
And even though building the try might take a bit longer up front, the speed gains during the search would make up for it, right? Especially if we're processing tons of sentences.
Exactly. Plus, remember that hybrid approach we were talking about? If those long words share common prefixes that also happen to be valid root words, a hybrid solution could be super powerful.
It's like we've got a solution for every kind of dictionary out there. But before we wrap this up, I want to bring up something that often gets overlooked when we're obsessed with efficiency.
Oh, what's that?
Code readability. It might not be as glamorous as optimizing speed and memory, but it's super important in the real world.
You're so right. Writing clean, understandable code is crucial for working with others, keeping your code manageable, and even just for yourself when you look back at it later.
Totally. So where do our different approaches stand in terms of readability? Which one would be easiest for another developer to understand?
Well, the hash set is probably the simplest to implement and read. The logic is pretty straightforward. Go through the words, check the prefixes, and replace if you find a match. Simple.
Like a clear set of instructions, no fancy data structures to figure out.
Now, the try, while super efficient, can be a bit more complex to code and understand, especially for someone who's never seen a try before.
Yeah, there's more going on behind the scenes with that tree structure.
Yeah.
Elegant, but maybe not as easy to grasp right away.
And as you might guess, the hybrid approach falls somewhere in between. Probably more complex than the pure hash set approach, but simpler than a full-blown try.
So how we choose might also depend on how experienced our team is and how important it is to keep the code super simple.
For sure. Sometimes a slightly less efficient solution that's easy to understand and maintain is the best choice in real-world projects. It's all about finding the right balance.
Well said. It's a good reminder that algorithm design isn't just about finding the absolute best solution. It's about finding the best solution for the specific situation you're in.
Absolutely. It's about weighing the options, considering all the factors, and making a smart choice.
Well, everyone, we've covered a ton of ground in this deep dive. From brute force to hash sets and tries, from hybrid solutions to analyzing dictionaries and thinking about code readability. We've looked at this word replacement problem from every angle.
It's been an awesome journey exploring algorithms and data structures, all starting from a seemingly simple problem.
And I hope our listeners are leaving with a better understanding of how powerful algorithm design can be, and that they've got some new tools in their coding toolkit.
Remember, there's always more to learn, more to discover, and even more elegant solutions out there waiting to be found.
So keep experimenting, keep pushing yourselves, and keep that passion for algorithms burning. Thanks for joining us on AI.Code.Cast.
We'll see you in the next episode.
And we're back for the final part of our deep dive into word replacement.
Ready to wrap up our epic exploration?
You bet. We left everyone on a cliffhanger last time.
Talking about combining hash sets and tries?
Exactly. Could we get the speed of a hash set and the efficiency of a try all in one?
It's a really interesting idea. Maybe we could use the hash set to quickly check if a prefix is a valid root word, and then use the try to actually do the replacement.
Like a two-step process.
You
I like
could.
it. But before we get too deep into that, we also talked about how the dictionary itself can influence our choice.
Oh yeah, for sure. The structure of the data can make a big difference in which algorithm performs best.
So let's say we have a dictionary filled with mostly short words, like 2 or 3 letters each. Would that change our thinking?
Totally. In that case, the hash set might be the clear winner. Remember, creating the hash set has a one-time cost, but if the words are short, the try wouldn't have much room to show off its prefix sharing efficiency.
So the overhead of building a try wouldn't be worth it with a bunch of short words.
Right, and the hash set's constant time lookups would be super fast in that scenario.
Makes sense. It's all about choosing the right tool for the job. What about the opposite? A dictionary full of really long words, like maybe some scientific terms.
Now that's where the try would really shine. Longer words mean more shared prefixes, and that's where the try's space efficiency really pays off.
And even though building a try might take a bit more time at the beginning, the speed we gain during the search would probably outweigh that cost.
Exactly. Especially if we're working with tons of sentences. Plus, don't forget about that hybrid approach we were brainstorming. If those long words have lots of shared prefixes that are also valid root words, a hybrid solution could be super powerful.
It's like we've got a solution for every kind of dictionary. But before we wrap up this epic deep dive, I want to talk about one more thing that's often overlooked.
Oh, what's that?
Code readability. I know it's not as exciting as optimizing for speed and memory, but it's crucial in real-world projects.
You're so right. Writing clear, understandable code is super important for collaboration, maintainability, and even just for your own sanity when you come back to your code later.
Totally. So how do our approaches stack up in terms of readability? Which one is easiest to understand?
Well, the hash set approach is probably the most straightforward. The logic is pretty simple. Loop through the words, check prefixes, and replace if you find a match. Easy peasy.
Like a clear set of instructions. No complicated data structures to figure out.
Now, the try, while super efficient, can be a bit more complex to code and understand, especially for someone who hasn't worked with tries before.
There's definitely more going on with that tree structure. Elegant, but maybe not as accessible.
And as you might guess, the hybrid approach falls somewhere in between. Probably more complex than the pure hash set approach, but simpler than a full-on try.
So our choice might also depend on how experienced our team is, and how important it is to keep the code simple and easy to maintain.
Absolutely. Sometimes a slightly less efficient solution that's easier to understand and maintain is the better choice in a real project. It's all about balance.
Well said. Algorithm design isn't just about finding the absolute best solution. It's about finding the best solution for the specific situation.
Couldn't agree more. It's about making smart choices, considering all the factors.
Well, folks, that's a wrap on our deep dive into the word replacement challenge.
We covered a ton of ground today.
From brute force to hash sets and tries, from hybrid solutions to analyzing dictionaries, and even code readability. We've seen it all.
It's been a blast exploring algorithms and data structures, all starting from one simple problem.
And I hope everyone listening is walking away with a deeper understanding of how awesome algorithm design can be, and hopefully some new tools for their coding toolkit.
Always remember, there's always more to learn and explore. There are even more elegant solutions out there waiting to be discovered.
So keep experimenting, keep challenging yourselves, and keep that algorithmic fire burning bright. Thanks for joining us on AI.Code.Cast. We'll catch you next time.